Next, we'll move on to our second type of example when we're working with the goodness of fit test. And this is a scenario where the individual probabilities for each category are hypothesized to depend on a smaller number of parameters, say theta 1 up to theta t, where t is specifically less than k. In which case, a specific hypothesis involving those theta values yields specific probability values, which are then used in the chi-square test. So this method is going to involve the same null and alternative hypotheses as the previous type of examples, and we're also going to compute the test statistic in the same way. However, now when we compute our degrees of freedom, it's going to be found using k minus t minus 1. And t here is the number of parameters that are estimated by our sample data, and k will be the number of terms in the sum, or in other words, the number of categories for the random variable. If we think back to that previous example where the degrees of freedom were one less than the number of categories, that's consistent with this definition, because when you think about that last example, the probabilities that we computed for each category were done so using the parameters for the hypothesized distribution, but we did not need to estimate those parameters. So, in other words, for that last example, t would have been 0, and if t is 0, then degrees of freedom would just be k minus 1. So that degrees of freedom formula is consistent with this one here. So let's look at an example. The data in the table on the next slide are frequency counts for 400 observations on the number of bacterial colonies within the field of a microscope using samples of milk film. And we want to test at the 5% level of significance whether or not there is sufficient evidence to claim that the data do not fit a Poisson distribution. So to start, our hypotheses are as follows. X fits a Poisson distribution versus X does not fit a Poisson distribution. Notice here that my null hypothesis is what we might call a composite hypothesis, because I'm not specifying a value for the parameter lambda for the Poisson distribution. And that's because in order to do this problem, I'm going to have to estimate lambda based upon the sample data in the table. So here's the table. We've got X equal to the number of colonies per field, anywhere from 0 to 11 colonies, and then a big gap. The next number of colonies in the field is 19, and since we don't see any other numbers in that first column, then that means there were no other possible values for the colonies per field when this data was gathered. And then we have the associated observed frequencies. Now, remember I mentioned that we needed to estimate the Poisson parameter lambda. To do that, what we'll do is we'll take each X value, multiply it by its associated observed frequency, add up those values over all possible categories that we've got here, and then divide by the total number of observations, which is 400. This is effectively the computation of a mean, but we're making use of a frequency table to compute a mean. In other words, instead of having a sum of 400 numbers, we're making use of the fact that 56 of those numbers in that sum are zeros, 104 of the numbers in that sum are ones, 80 numbers in that sum are twos, and so on. And so we can come up with an estimated value for lambda, we'll call lambda hat, which is 2.44, which we get by performing that operation. Next, we need to generate the probabilities associated with each category for our random variable. To do this, we need to make use of our Poisson probability distribution. In particular, you might recall that for the Poisson distribution, the probability that x is equal to x is going to be given by lambda to the x e to the negative lambda over x factorial, and these are for x values ranging from 0, 1, 2, and so on. So, in particular, say we look at our first value for the non-zero number of colonies per field, where we're looking at the probability that x is equal to 1. This is going to be our lambda. We're going to use lambda hat, so 2.44 raised to the 1 power e to the negative 2.44 all over 1 factorial. If we do that, we'll get 0.213. Similarly, we do that for every possible category here, including where x is equal to 0, and we generate the following probabilities that you'll see on the next slide. But then notice also we can compute our expected frequencies. So if I want the expected frequency for when x is equal to 1, I'm going to take my 400 observations and multiply by 0.213. and we'll get 85.07. So that will be the corresponding expected value for when x is equal to 1. And again, we'll do that for all possible categories, and we can complete our table as follows. You may recall from section 13.7 when we were talking about the chi-square test for independence, we were worried about situations where the expected frequencies were less than 5. We share that same concern here, which is why I have all of these numbers highlighted in red. One of the other things we might notice, though, I might go back and just point this out, is that the sum of the probabilities should equal 1. In here, I've got it equal to 1.00094, and that's due to the round-off error that I've made when I've been computing these probabilities. And the sum of expected frequencies should also equal the total number of observed frequencies, which is 400. Again, here, my expected frequencies only equal 399.98. That's due to round-off error as well. So the greater concern that we have to be focused on are these expected frequencies, which are less than 5. So what we'll do then is we'll collapse all of these categories into one category. We'll call this the category which corresponds to being 7 or more. And we'll take those expected frequencies and add them up. They should be 5.04. Technically, if you add up the numbers that I've got here in red, it equals something like 5.02, but again, I want this all to equal 400, so I'm just going to change that to 5.04 so that my sum does equal 400. We'll combine these observed frequencies together as well to get 20 here. We get the following table, which now has fewer categories, but now each of my expected frequencies is now at least 5, and you'll notice that this probability here is associated with 1 minus the sum of these probabilities. Now we can compute our test statistic. We are summing over categories 1 through 8, and we have the observed minus the expected squared divided by the associated expected value. If we do that for all 8 categories, we will get 74.87. Now when we go to decide on our degrees of freedom for our rejection region, remember K corresponded to the number of categories, T corresponds to the number of parameters estimated by the data. Since we estimated lambda, that makes T equal to 1, so our degrees of freedom are 8 minus 1, which gives us 6. If we look up the chi-square critical value with an area of 0.05 in the right tail with 6 degrees of freedom, we get 12.592. Our test statistic is clearly in the rejection region, and since it's so large by comparison to this critical value, that tells us that we have strong evidence to suggest that the data do not fit the Poisson distribution. This completes our discussion of the goodness of fit test associated with the chi-square distribution of section 13.8. Thank you.